As usually, before I will start, could you confirm that you can hear me, please?
Yes, sir.
Yes, we can.
Okay, thank you very much for this. So today we will continue with this Diversitas with Mathematica, and before we switch to slides, I would like to show something what I have promised to several of you during the laboratory, but I think that this is quite useful to watch it by everybody. So as you could see, we during the laboratories have simulated behavior of some dynamical systems. So mainly that were oscillators, but recently on the last term, we switched to simulate the behavior of some kinematic car. So in general, we can simulate the behavior of vehicles. And having such models of vehicles which we were working with, you have had provided there the model of a kinematic car and also of a kinematic car with a trailer. Having such models, you can elaborate for such systems the control algorithms. And since these systems are non-holonomic in the sense that there are the directions in the workspace of this system into which you cannot move directly. So you cannot move with your car directly to the right, to the left. You can go only straight ahead or backward, and eventually you will obtain a side position when you make some turns in order, like in the parallel parking problem. And those of you who know, who have tried to drive the car with a trailer, know probably how difficult it is to park reversely, to make the revert parking with a trailer. When you have to go backward, your trailer behaves opposite to this what your car does, and this is not very easy. However, it is possible, of course, to park. You have to have simply some training, and then you will be able to do this. And of course, there are some algorithms which describe what is the procedure of reverse parking, how you should perform when you have a trailer in your car. And moreover, there are some generalization of such algorithms which say us how to do this when you have several trailers. So what I'm going to show you just in short, this is just the results of some experiments showing that when you have such models, you are able to elaborate the algorithms which allow you to park some difficult to control or allow you to control some difficult to control devices. So let me share the screen and I will shortly describe what you can see there. Just a moment. Where is it? Okay. Okay, so this what you can see now, this is the setup of the experiment which was conducted to show how such parking algorithm will work. So what you can see here, this is just a set of a tractor, the propelling the whole stuff element, and to this tractor there are attached 3 trailers. So this is the only unit you can control directly. You drive it simply. You can, this is the case when you have two steering, you have 2 wheels, and you can set up the velocity of each wheel separately. So this is a kind of a simplified car, one can say. Okay, anyhow, when you would like to go forward, it is quite easy because when your tractor will run somehow, then trailers will follow the path of it. But when you would like to go reverse, then there is quite large problem, because very soon you will get the situation that the trace of movement of the last trailer will be out of your control. And here is the experiment which shows that applying the appropriate algorithms, you can control even such complicated case when you have 3 trailers attached to your pulling device. So the task is that this is the last trailer and you want to park this exactly in this place. So you have to go in such a way with your propelling tractor to get this last trailer to be placed here in this box. And this is the video taped with real experiments. So you can see that this algorithm I'm talking about is working also in reality. So let's see what will happen. So you can see that at the very beginning, our tractor is going left and right, turning just to obtain the proper configuration of the trailers which it has attached. And after some time, you can see it can push back the trailers in such a way that this last trailer is getting exactly to the box we wanted it to be. Okay, so now our experiment finished and we have got this. Here you have the same example, but with more difficult initial position. So now we are put perpendicular to this place, but you can see that even in this case, our algorithm is able to control the car, the vehicle movements. So now again, we are turning left and right to get the proper configuration of our trailers. And after some time, you will see that we will be able to drive the system exactly along the path we would like to. So when you make such simulations like we did, you are able to investigate the behavior of your system, and then you are able to think about the algorithms which allow you to control the vehicle. Okay, so this algorithm doesn't care about the final configuration of the rest of your setup. The only important thing is that the last trailer should be placed in the box it is ordered to. So there are, of course, algorithms which allow you also to, for example, line up all the stuff or set it in a prescribed configuration. So you can also solve more complicated case. This is the next video. Here is the situation that the box you are trying to park is moving. So simply you would like to follow a trajectory. So here you will observe how the trajectory evaluates along the time, and we would like to catch up this element with our trailer and just follow it exactly like it is. So one can say that now at the initial condition, we have some initial error in the sense that the trailer is not at the place we would like it to be. And after some time, this error will get smaller, hopefully will get to 0, and then we will follow exactly the point we would like to follow. Okay, so let's observe what is going on here. You see, as time is passing, the desired position changes. And of course, the algorithm has to know what is the trajectory to follow. So this is the input to our control algorithm. But you can see that even in this case, it was possible to get there, and you can see how the tractor is maneuvering left and right to get the right position and orientation of the final trailer. Okay, so this is the last video I would like to show. This is more complicated case comparing to the previous one. Here we have 8-shaped trajectory. So this is one of the Lissajous curve to be followed. Okay, so this is the part of it. So you can see that it is possible to do things which are not in the range of things to be done by humans. So there is nobody who is able to drive backward with 3 trailers.
I'm sorry?
Yes?
But this is a mathematical solution for this problem, right? It's not intelligence, like machine learning.
This is just actually it is not important if it is done in Mathematica or not, but basing on the model of the car with trailers, similar to this one which we were working with, somebody has elaborated the mathematical formulas for this algorithm. So we have closed form solution, which simply says what should be the control if you would like to follow such trajectory. So this is elaborated on the basis of the higher mathematics. Here is the Lie algebra used, and basing on some manifolds which are introduced with this Lie algebra, the solution is elaborated. This is just the algorithm, how to control this. We will try to work with such simple algorithms on our last laboratory. I will explain this in a moment shortly, what you will be expected to be done. But of course, you could try also to solve such problems with some modern, let's say, technologies like artificial intelligence or neural networks or genetic algorithms or machine learning. There are several of them, but it is huge amount of computation to find out such a solution. And of course, when you have problems which you are not able to solve with a traditional methodology, then you should switch to these modern methods, but it doesn't make sense to apply the artificial intelligence, for example, when you have such closed loop solutions. Nobody will do this for typical simple tasks which we already know how to solve. So this is just the model-based solution, one would say. Solutions get with the neural networks or artificial intelligence usually depend on the observation of the behavior of a system, making some approximations of it, and then just finding the solution by experience you got. Okay, so now we can switch to our slides. Okay, so to be honest, I don't remember exactly where we have finished last time. Wait a moment. There is no my window. Just a moment. Okay, that's it. Okay, probably you now see the window with the Mathematica slides. So for sure we were talking about work methodology, and I recommended you to work usually with two notebooks. One is the main area of your work, and the second one is for the scratches, just to try something, to examine parts of your expressions. So this is what you should remember. I was also talking a few words, and I will repeat because this is the powerful mechanism implemented in Mathematica, that you can have the variables which are dynamical, and it doesn't mean that what in typical programming languages, but it means that they will compute their values automatically. So every time when elements on which the variables depend changes, then the variable will update its value. So this is powerful, but also quite a dangerous mechanism. So you should use it very carefully. Unfortunately, I won't cover this topic here during our lessons because there is no actually time for it. Okay, I don't know what happened. Sorry for this. I have made the window larger, and then sharing disappeared. So I'll try to share it again. Okay, so since I'm going to cover some side elements, some side topics considering the Mathematica, so let's try to look to the elements some of you have already learned, because I have seen during the laboratories that you have prepared such graphics, for example, like this one I'm going to show in a moment, but for some of you that will be new, and also I'm pretty sure that there will be some more elements which will be new for you. So here we have the example what we already did, where we simulate the behavior of some dynamical system. So this ODE1, this is our dynamical system with initials. We have the solution, and we plot it simply like we did. At the moment, no animation, but simple time plots for some initial conditions. So here you can see that we can plot the position of the system as well as the position, velocity, acceleration. So we will get this like it is. Of course, you can plot it in the phase plane. Actually, just recently, I have added to, let me check where it is. I have added to our web page. Where is it? Okay, when you go to the web page of our course, to the table with the laboratory classes, so in the laboratory number 3, Odes in Mathematica, I have added some nice illustration of the face portrait. So probably those of you who don't understand until now what is this phase portrait we are working with. We'll see how it works with simple pendulums, with simple oscillators, and also very nice illustration of chaotic behavior. What we were going to do, but because of my mistake, we haven't done it. So just if you are interested in, look to this quite short video, and I think that everything will be clear at the moment. Okay, so using this parametric plot, we can plot our phase portrait, but if you would like to see how such system behaves for different time and for different initial conditions, we can make a manipulate module, which allows us to change interactively some stuff. So here we have defined the solution again, and solution to our system. I put it directly to ndsolve, but of course you could put it in a separate variable, and then we are executing parametric plot with time which is specified by a slider which is provided in our manipulate block, and also with the initial position, which here is the P of 1 and P of 2, which will be determined by our locator. And this locator will change in the range which is assigned with some initial value. So at the beginning, the initial value of our locator is 2 and 1. So when we run this manipulate block, you can see that first of all, we can make longer and shorter period of the simulation. Since this is the system with no friction, you can see that simply we will get longer and shorter actually closed path, part of it, or the whole. Now it looks like nothing has changed, but just the trajectory overlaps, and you can plot it. You have plotted several times on the same part, but you can also here change this locator, and for this locator you will see how the system behaves. So for these initial conditions, when we have such behavior like you can observe here, we have simply the oscillations. So the oscillator is going back and forth. You can imagine that this is just a pendulum which just make these oscillations. But when you give the larger initial value of the velocity and the position, then you can see that your pendulum starts to rotate. You can see that now it is so that the position constantly changes to positive values, because the initial velocity was so large that the pendulum started to rotate instead of oscillations. So here you can imagine, maybe we can make this longer. So here you can imagine how this portrait looks like. So somewhere here you have the stability points. When you start with this point, you simply will stay in this point forever. But if you move a little bit away from this point, you start with small oscillations with small amplitude and small velocities. When your initial position is a little bit far away from the stability point, then you can see that the oscillations are larger and velocity of the movement is also larger, and then you will get this situation that the position is such. Actually, I have also here some initial velocity. Maybe I will start with this initial velocity. So you can see when you are moving to the left, at some point when you get to this equilibrium point, which is unstable, then you can get this behavior that you start to rotate. So with this tool, you can simply simulate and analyze the behavior of your system. Of course, if the system is more complicated, you have to have quite powerful computer to run this in real time, because every time when you move this locator, the Mathematica has to solve these differential equations. So it takes time. Okay, so here, this is just the example taken from the web page of Mathematica of Wolfram, and here we have the situation where we have some more complicated system. So maybe it is not important to look at the system at the moment, but it is described with this equation. And then here on this plot, you have combined the vector field, which is connected with such a dynamical system. The vector field, this is just the field of vectors, which shows in which direction we will flow in the given region. So let's set the time to a very small value. So you can see that, for example, when I'm setting values like this, so I'm going along these vector fields. So now you can see that time is quite short. What it is, just 1. So I'm going here with quite large velocity. So I have passed quite long distance. But when I start with my movement a little bit lower, you can see that I haven't got much further, but because the velocity has changed actually. So these arrows doesn't show the velocity which is here, they show only the direction of the movement. So if I start, for example, from this place, you can see that also these movements are here. Here is just the symmetrical situation, and here are some elements where I can start, in some sense, rotate. So you can see that, for example, when I start with this point and I will make my time longer, so I'm getting here some kind of a closed orbit. I'm going around. This is not exactly the closed case orbit, but you can see that this is what I can get here. So now you can examine where will you finish, what kind of movement you will obtain, starting with different initial positions. So you can see that this system has a kind of stable orbit, because no matter where I start from, I finish with this orbit on which I'm going here around. Okay, so here we have the same computation made with some additional elements, in the sense that this is more colorful. If it will be, okay, Mathematica is running, so I hope that it will be able to compute it in a reasonable time. But maybe what I can show you with this system is to add to this system some friction. So let's assume that there is arbitrary friction proportional to the velocity, and on this side it has to be with plus. y prime of t. Okay, so unfortunately, Mathematica is not able to compute it in a reasonable time. It has already computed. Yeah, but I have pressed this twice, and this is why it is computing. So you can see that you can get this in very colorful way and get your trajectory plotted on your vector field illustrated with colors. Okay, so unfortunately I have, as I say, I have pressed this several times by accident, and Mathematica was recomputing this stuff. So let's try to compute it. I don't know if this friction is quite large. So maybe let's make a little bit smaller friction. Okay, so now you can see that starting from some point, the oscillations disappeared because there is some friction which consumes the energy from our system, and finally system stops. So as you could see previously that you have had these sinusoidal oscillations. Let's return to this example, what we have just a moment ago. Okay, so when you start, for example, with this point, you will get the rotation forever because there is enough energy to rotate and the energy of the system doesn't change. But if we add some friction, so then you will observe that starting from a similar point, you will finish finally somewhere in some equilibrium. So now you are rotating, energy is getting smaller, so the velocity of movement is smaller, and then after some time you have no enough energy to rotate next time, and you finish in some equilibrium. So for example, when I make smaller initial velocity, I will get closer. So here I have got 3 rotations, here I have 2 rotations, and here is no rotation because I simply oscillate. So you can see that this system behaves in such a manner. So you can learn about the behavior of the system on the basis of the phase portrait. Okay, so let's switch to the next topic. Now I would like to show you some elements which are connected with graphics in Mathematica, but outside the field of this what we have studied. So for example, when you are going to be a medicine doctor, then you can use Mathematica to study anatomy. For example, here are examples of some skeleton with some additional elements. So if you are interested in such elements, you can go to the Wolfram page where you will see what you can analyze with anatomical structures in Mathematica. So the next element we are having here are connected with this artificial intelligence and neural networks. So if you are interested in working with neural networks, you of course can do this also in Mathematica. And I'm not very familiar with neural network, but as far as I understand, this is the example where I will train the neural network to recognize some digits. So here I have taken some exemplary data from the resources which Mathematica is providing. Okay, so these data were reading from the databases of Mathematica, and I can see how looks the training samples. So there you have some training samples. They are chosen randomly. So this is handwriting of 8, 1, 6, and so on. And our neural network has to learn and recognize these digits which are handwritten. Okay, so you can see how it looks like. For example, you have different samples for the same value. This is the handwriting of some set of people. So now you have to define the network which will try to learn this. I don't know what is the structure of this network. As I said, I have simply taken this example from the examples. Next, you can train the network, sorry, with some data. Okay, so here you can even see that you have some visualization of the progress of this training. I hope that we can stop this training. We can stop this training at some time. Okay, so now the network, I hope, was trained somehow, and now you can evaluate and see how Mathematica is recognizing your elements. So here again, you are putting some inputs, and you can see that after such short period of training, even the Mathematica can recognize this. Okay, so on the Mathematica web page, you will find another example of classification and in this example, you are able to provide the live handwriting digits, and Mathematica will recognize this online. Considering the classifications, you can see that you have several different functions which allow you to make such kind of classifiers, and actually the neural networks, this is one of the most popular applications to classify the data, to make the recognition. This is how it is. Okay, so if you are interested in working with social medias, you can also do it with Mathematica. So you can connect to any oops, I have to quit kernel, probably something what we have defined previously. Doesn't allow. Okay, actually my window with okay, maybe I should show you my whole desktop. Just a moment, please. I cannot get, okay, it's up there. Sorry, I have forgotten. Okay, so at the moment when I have tried to connect, to run this service connect, then my web page switched to Flickr, but unfortunately I don't have the account on this service, so I will show you what is illustrated with doing such thing on the Wolfram web page. So for example, you can connect to any of the social media you are using, and then you can get some IDs of the Flickr users. Then, for example, you can construct album of links from these IDs, and then you can construct the links to all images in these albums and import them their metadata. So you will get the information about these pictures, in what conditions it was done, what was the aperture, what was the in general camera settings, what is the date, and some tags which are associated with the data you have just gathered from the social web page. Okay, so then when you have imported all this stuff, you can make a different kind of statistics on it. You can analyze this in many different ways. So for example, you can get the date histogram. So you will learn what was the time of the day when the picture was taken the most frequently. So you can see that evenings are the times when the Flickr's pictures are taken more frequently. For example, you can display the normalized frequency of taking the pictures among the series of the years. So you can see how this changes. For example, you can make a summary visualization of different tags. So you can summarize how often different aperture value of the lenses were used, what was the exposure time used the most frequency, what is the ISO rate of the setting which were applied, and so on and so forth. So you can analyze this in many different things. So you can make a statistics what kind of camera or what kind of lenses were taken with the elements. Here also on this page, the link to this page is provided in slides I have prepared, so you can see that there you have some more related topics, and for example you can simulate different time of day using color balancing with Mathematica. You can perform some color tone mapping, or just do any other stuff with your images. So it is possible to work with Mathematica as a image processor, which allows you to change the elements, and what is most important, you can program what kind of changes you would like to do. So I'm not saying that it can work like a Photoshop, for example, or any other stuff to edit the pictures, but if you have some standard normalizations of the pictures you are usually performing, you can automate the execution of them by preparing some Mathematica programs and then executing these programs on your pictures. Okay, so let's switch to next examples. So maybe we will stay here. Okay, so another topic which I have already talked to you about it very shortly at the beginning is just the geographical data which are collected in Mathematica. And let's try to work with some examples what you can do in Mathematica with this data. So let's read in information about Wrocław and Poland. We will be interested in these two elements, and for example, when you would like to learn what is the population of Wrocław, you will see the number. I don't know if it is actual and how often this is evaluated, but for example, when we would like to learn what was the population in year 205, then Mathematica will provide you a slightly different number. So let's say we will be interested in okay, there is no data available. Let's see, 90. Okay, so 20 years ago, it was something like this. There were more people than they are now. Okay, so, okay, I have the example here, which is prepared for the range of dates. So we can see that the data starts from 1976. This is the first time, but for quite a long period, this is something probably estimated because this value doesn't change at the beginning. Okay, but anyhow, you have at least And of course, when you have such data, you can simply plot it with a list plot, what we have already done several times. So you can see how it has changed during these last 40 years, let's say. Okay, so what else you can learn about such a place is just given to you when you see what are the properties of a given entity. And here you can see what you can get, what kind of information in which field you can get about Wrocław. So at the moment, these entity properties are set and you can work with them like you did with any other data. Okay, so next element is also connected with geography. What's going on? Okay, so if you would like to enter all this kind of stuff, you can, first of all, you have to move in time. So you have to formulate the date object. And as you can see, it is provided to you by the date object function. And then when you have this date object, then you can specify the entities like we did on the previous slide. So of course you can use different formats. Here is just the example where you are using the standard Notion. And for example, here I have used it to compute how many seconds has passed from the beginning of the epocha in computer science. You know probably that this is the 1st of March of 1970 when everything started to be counted, because nowadays it is a problem to stamp the material with a uniform unique date, which will tell you which material is younger, which material is older. When people decided to make this in such universal methodology. So, okay, so now you can see that this is 1,6 times 10 to 9 seconds, which was passed from the beginning of the epoch. And altogether, this is 1858, 80,582 days. Okay, so if you would like to switch to entities, then you can use the entity value function, which I have already used, but you can also use the freeform input. So if you would like to make some input in freeform in Mathematica, let's open new notebook to show you this. Simply, when you are not in a cell, just you have to type the equal sign, and now you can describe in the natural language what you would like to get. So plot of sine function. And then Mathematica will try to do it for you in the way like it is. What's wrong with this? It is computing. Okay, so we have got it. So exactly the same way like you would get the input which you put into the Wolfram Alpha page, it is also possible to work with your Mathematica in the same way. So if you don't know how to get some stuff, maybe you can try this free format input. Just remember that this equal sign has to be typed outside of the cell. If you are inside the cell, then it won't work. Okay, so I wanted to get some information about the Forest Gump, and Mathematica has connected this with Forest Glen, unfortunately. So you can see what kind of information you are getting in such a case. There is quite a lot of it. And this all is in the form you can elaborate with Mathematica. So all this data can be manipulated with your formulas you would like to get. And I've got this Forest Glen because I have misspelled this Forest Gump, and now when I put this correctly, so you can see that this is a kind of a internet movie database where you can learn a little bit at least about this movie, for example. So there are plenty different information. Actually, Mathematica is covering this information from the external web pages, but what is the most important, it is providing you this information in such a format when you can make a computation on it. So this is, I think, interesting ability of Mathematica. So if you would like to get some more information, go to Ref Movie Data, and then you will see these examples. Okay, and now there is these examples which I was thinking about, this geographical one, where, for example, we can get the list of largest or large cities in Poland in the sense which Mathematica is defining this. So let's wait a moment. We will see if anything has changed from that time. I have run this last time. Okay, still 39. Okay, and here, for example, is the function which allows you to get the roadmap connecting, in this case, Wrocław with all other cities. Okay, so I actually I'm not quite sure if I should run this because I don't know how long it will take to compute it on my computer, but you can see that on the base of this analysis, you can get such a kind of dendrit, or how to call it, and you can see that there are mainly 1, 2, 3, 4, 5 directions in which you go when you want to reach from Wrocław large cities in Poland. So you can see what is the roadmap actually connecting Wrocław with these places. So since it haven't taken very long, not like this. I haven't read in any other cities, so probably it is no why it isn't here. But you can try to change it for any different city, and you will get this the same way. Okay, so this is more or less everything what I wanted to say you about the Mathematica. When we met last time, I asked you to think if you don't have any subjects you would like to cover, or if there is something you missed or you don't understand, I could repeat. So we have some time to do this, and I also will try to say a few words about the last exercise which we will work with, but this I will say in a moment. So do you have any questions, any problems? You would like anything from me to explain again or just additionally? Okay, are you there still?
Yes.
That's nice. Okay, so let me show the last description. I will put it just in a moment on a web page. So let me show the task I would like to do at the last laboratory, and it will be a kind of a final test, one can say, which I would like to see how you are dealing with. So this person who were worked during the semester in such a way that I have seen quite a lot of solutions to the task we were working will simply get the mark on the basis of this. But for those of you who have shown not much, but there are a few people who have shown almost nothing, I would like first of all to see how you will deal with this final task. And also for these who have shown not much, I would like to see how you will deal with the exercises we were working during the semester. So probably I won't be able to talk to everybody on the last laboratory. So this is not this week, this Friday, by the next Friday. This Friday we will finish working with this kinematic car and kinematic car with trailer. So those of you who has done it already can start thinking about the final exercise. Okay, so let me share the screen again. Okay, so let's start. There are two exercises prepared, and let's start with the second one, which is, one can think, more complicated, but since we were working with the double pendulum quite a lot, I think that it will be quite easy to you to work with this example. So the situation is as we have previously, but we have simply double pendulum. The difference is one small, that in another way the θ2 angle is measured than it was previously. Or maybe it was like this, I can't remember. Okay, so we have a vertical line and we will measure the position of the pendulum counting to this line. So we have θ1 from the y-axis to the first link, and we have θ2 from line parallel to y-axis and to link L2. Okay, so as you could see, we have elaborated a model of this pendulum, and previously we have derived this model directly from the rule of motion laws given by Newton, and here this is just provided as the input to our task. So this is exactly the same model we have elaborated there, but here it is recalled in the full form. But previously what we did was that on the left-hand side of the right-hand side of these formulas, we have had zeros. It was such the situation that it was a dynamical system with no controls, just free floating. Only the movement were caused by the gravity forces which are presented here on the Earth. And now we will change this system to be a control system, in the sense that we will apply two new variables, u1 and u2, which are our controls. We have already done such thing also when we wanted to observe some excitation of the systems. So we propose that the system will have some controls. In our case, with this double pendulum, this control is nothing else but the torque which is applied at the pendulum joints. So U1, it will be a torque in joint, in the first joint with the angle θ1, and U2, this is the torque which we apply with in the second joint θ2. So you can imagine that you have some electrical motors which drives your pendulum in this way, that the motors provide torques to the system. Okay, when you would look closer to this pendulum model, you will see that it has a special structure, that there is the matrix Q, which is nothing else but again, I have forgotten the English word, inertia matrix. I don't know why I'm just forgetting this just a moment before I'm going to say this. So this is the inertia matrix, which says how difficult it is to move your system. So this is the equivalent of the mass in a standard scalar one-dimensional equations. This inertia matrix is multiplied by the acceleration, and then you have additional element, a vector, which contains all other forces which are in your system, the gravity, the friction, or anything else which would appear in your model, centrifugal forces, for example, then they will be contained in this element. So it is quite easy to distinguish these elements from this system. And when you look to this equation and to the form you would like to obtain, you will find out that Q matrix has such a form, which is depicted here, and B vector has such a form, which is depicted just below. So what is for us important? On the base on modeling our system, we have obtained such a model. And now we can try to control the position of the tip of our double pendulum. So let's say that you can think that this double pendulum, this is a simple manipulator with 2 degrees of freedom, and here it has attached a gripper, a kind of effector, and it will operate on something. And you are interested in controlling the position of this tip. So first of all, you have to describe where your tip is. But we have already done this. We haven't done this very formally, but you remember for our animation, we have computed the position of this point, and also we have computed the position of this point, and then we have visualized them. So we simply will get this output map, output function, which says us where is what are the coordinates of the tip of our pendulum in the relation to the position in the angles. So this formula you already have seen. And now this formula has a format of the vector output. So this is just a function of our, let's say, configuration vector. So here we have defined the Q, which is the configuration vector, which contains these θ1 and θ2 elements, the internal coordinates of the system. Okay, so we are equipped with the dynamic model of the system and kinematic model of the system. So here we have the kinematic dependencies, here we have the dynamic dependencies. Okay, so now we are able to apply a control methodology, which is visualized in this figure, in figure number 2. So our plant, this is our manipulator, our double pendulum, and it produces output where the tip of the double pendulum is, and it is driven by our input, our controls, U. What you can do is to apply, this is one of the schemes, of course, you can apply, and here we are doing this the following way, that we are providing some preprocessor, some kind of linearization part, which on the basis on the new input V will compute the input U, which should drive our double pendulum. Then you have to compute somehow this input V, and this will be done with simple linear PD controller. And for us, it is important to know the formulas. I will show you this in a moment. So we will have some desired trajectory of our system. Let's say that the tip of the pendulum should move or on some kind of, I don't know, circle, ellipse, or any other curve. And to this PD controller, we also input the actual position. So we have to have somehow to measure this position. So in simulation, it is quite easy because you are calculating this position. But in reality, you have to have a tool which allow you to measure where your tip at the moment is. And these two input allow PD controller to compute this control V. How it is done, it is written here with formula 6. So you can see that on the basis of the difference between actual and desired position and velocity and desired acceleration, when you have desired trajectory, you have also velocities and accelerations, you are able to compute V. And here in equation 5, you have the formula which is realized by this linearization part. So you can see that you simply have to compute some matrix multiplications and multiply this by V, which was computed by your PD controller, and then you will obtain this U. So what is the methodology to work is the following. When you have a model in such a form, then you can compute on the basis on such a model the feedback control where you have to compute such formulas. Okay, so these formulas are provided here in 2 steps because here you have matrices D and P, which aren't provided directly here because here you have Q and B, but just below you can see that to compute D, you have to compute such a formula, and to compute P, you have to compute something longer, but actually this is just everything what you write in Mathematica in one row. You simply, having defined the matrices J, Q, and B, you simply compute what you need here. Just put the formulas, nothing else. Okay, so what I would like to do for you, just to simulate with Mathematica such a system. Okay, I can imagine that it can look very complicated, and if somebody wouldn't be able to deal with this system, can try to make something simpler, because there is prepared a task which is the task or controlling the inverted pendulum. And this is a modification of the pendulum we have already worked with, because it has the moving vertically base attached. So previously, this point along which our pendulum were rotating was placed at the 0 constantly. The pendulum hanged up there. But now, at the moment, we have the possibility to move this base up and down. So here is the Y parameter, which simply says where the base is at the moment. It can be at 0, So it will be our standard case, this what we were worked with, but you can move it also up and down. For example, oscillating this somehow. And you will find that this is quite interesting case when, with no reason, one can say this pendulum stabilizes at the vertical position. So it starts to oscillate along this vertical position, which everybody knows for pendulum is simply unstable. So the equation of the pendulum will be like this, in this form. And now for this pendulum, you will assume that you have the control in such a form. So simply as a y, you should put some oscillations. As you remember, we have already tried to find out the answers of the pendulum to some external excitement. It was a step function. Actually, we haven't done this during the laboratories, but there was such a task. Maybe some of you have done it for himself. And we have also analyzed what is the behavior of the pendulum when we have applied some oscillations. Actually, we were examining the resonance frequency of the pendulum, and we have seen that it is quite easy to drive the pendulum with the resonance frequency, but when you are out of the resonance frequency, then it is much harder to get large oscillations. So it was the main conclusion for the simulation which we have performed. Now we will try to work with our pendulum with higher frequencies to see what it does when you apply such higher frequencies. Here are some examples which you should try with your pendulum, and you simply should work with this, analyze this, and make your own conclusions about this, what is going here. Okay, so you have almost 2 weeks to prepare to these exercises. So look through them carefully, watch which is easier for you. We have actually worked on both the cases. That means that both of you should be you should be able to realize both of them, but of course you will choose which one you would like to work with. So you have to choose at least one. So this is what is important here. Okay, so be prepared for dealing with such a system. Read carefully through this, what is written here, and then when we will meet next time, there will be still time during the lecture, there will be still time to ask the questions, to learn more about these systems, and to analyze the cases you are provided. Okay, so maybe at the moment you have some questions.
Professor, could you please explain about the test again?
Once more?
Could you please explain about the test again, because I didn't hear everything you said about it.
I don't know. What do you want me to explain again?
About the test. You were talking about that we were going to have a test.
I was talking about the final exercise, which will be this test. So the last 20 minutes, I was talking about 2 examples, this double pendulum and single pendulum, and this will be used as these tests for the laboratory from the as a final task. And if you mean the test from the lecture, so I still don't know how it will be, because for the time being, until the end of November, we have to perform all the tasks remotely. And if it will change or not, it is hard to say. So what form of the test, final test from the lecture will be, it depends on the situation. if we will be able to meet locally or not.
Okay, thank you.
You are welcome.
So, if it's our last laboratory, I mean, this that you were explaining, so we won't have any else laboratories till the end of the semester?
Oh, no. This is, sorry. I have explained this at the beginning of the semester. This is the last laboratory concerning Mathematica. Next laboratories will be just the set of similar laboratories to work with the similar exercises, but with MATLAB. And it will be conducted by my colleague Mariusz Janiak.
Okay, thanks.
You're welcome. Okay, any other questions? If not, then thank you very much for being on this lecture, and we will see on Friday during the laboratories. See you then.
Thank you. Goodbye.
Goodbye.
Goodbye.